Good morning to all of you. We continue with our discussion on electrostatics. In the last lecture, we had introduced Gauss's law. So, let us recall that if you have a set of charges q1, q2, q3 etc., and if you have an imaginary surface, as we called it the Gaussian surface, then the flux, electric flux through this imaginary Gaussian surface is given by q1 plus q2 by epsilon 0. The electric flux through this closed surface is equal to the charge enclosed by the closed surface divided by epsilon 0. Please remember that the electric field at all points on the surface is the electric field generated by all the charges in the system, including q3 here. So, electric field at this point is the sum of electric field because of q1, q2 and q3, while in the flux equation the total flux crossing this Gaussian surface is equal to the total charge enclosed by the Gaussian surface divided by epsilon 0. So, the charges could be positive or negative. So, we have to keep track of the sign of the charges here. So, if q2 happens to be equal to minus q1, the net flux becomes 0. So, please remember that a net flux is equal to 0 does not imply no charges present in the system. We can have 0 flux because of cancellation of positive and negative charges, or because of no charge being inside the surface. We generalize this to say that the total flux through any Gaussian surface is the sum of all the charges present within the surface divided by epsilon 0, and in fact, if you have, so the flux was defined as if you have a surface, the flux we had defined as E dot ds. So, if I had a surface ds here, ds vector, and electric field was like this, then the flux through this ds is actually E dot ds. So, this is for a set of point charges. I can actually generalize this into an integral form. The total flux is actually integral E dot dA, which is equal to charge enclosed by epsilon 0. This is an integral over area of the Gaussian surface, and this circle on the integral sign implies it is a closed integral. So, it means the entire surface, the surface is supposed to be closed. So, the net flux emanating from the closed surface is charge enclosed by epsilon 0. So, if you have an arbitrary surface, you take the E dot dA, you take the element of area at every point, calculate the electric field at that point, integrate, and finally, you get the total flux coming out of the surface must be equal to charge enclosed by epsilon 0. So, this equation is true for any surface, any closed surface. It is the charge enclosed includes all positive and negative charges within the surface, and I must emphasize again that the electric field which is existing in this equation here is the total electric field produced by all charges. The Gaussian surface is an imaginary surface. So, I can choose any arbitrary surface as a Gaussian surface. In problems, I will choose a Gaussian surface which will help me to resolve or calculate the electric field, etc. And so, the choice of the Gaussian surface depends on the symmetry in the problem. So, we will discuss some examples where it will be obvious the kind of Gaussian surfaces I will choose. So, Gauss law is very useful when there are symmetries present in the system. Gauss law is always valid. It becomes useful for me to calculate electric field for a given charge distribution or the charge distribution for a given electric field when there is symmetry in the system. And as I mentioned in the last lecture, the Gauss law is based on the inverse square law of the electric field. So, all fields which behave like an inverse square law will satisfy this. So, for example, gravitational field also will satisfy an equation like a Gauss's law, and this law is valid for any distribution of charge and any Gaussian surface. So, in the last class what we did was we used this law to consider where the charges are there in a conductor. So, if I had a conductor, we considered an arbitrary conductor, solid conductor here, and we put an excess charge q, and we were trying to find out where the charges are sitting. Are they within the meat of the conductor, or are they on the surface, or are they in both places? So, we used Gauss's law, and because the electric field inside the conductor has to be 0 at all points, because if there was electric field then the charges would move, and in a static situation there cannot be any electric field within the conductor. So, we use this fact and we took Gaussian surfaces inside the conductor, and because the electric field at all points on the surface is 0, the net flux is 0, and then you can actually shrink the surface, the sphere, to a smaller and smaller values. The charge continues to be 0, and finally you will reach a point, and that means there can be no charge within the conductor. So, you can take Gaussian surfaces at different points and you can show that there are no charges within the conductor, all the charges are distributed on the surface, the charge, excess charge is at the surface. So, the charge distribution at the surface is such that the net electric field within the conductor becomes 0. So, if you have an arbitrary charged conductor, the charges are not necessarily uniformly distributed on the surface. You may have less charge here, more charge here, etc., etc. So, charge distribution actually adjusts itself in such a fashion that the electric field within the conductor is 0. If you had a cavity within the conductor, suppose I had a conductor here and I had a cavity. So, this is the conductor. The question is, are there charges on the inner surface of the conductor? Now, one can show through arguments that even the inner surface there are no charges. I can take a Gaussian surface like this, enclosing the cavity, and because the electric field at all these points is 0, the net charge enclosed by this sphere must be 0, but I could have equal amount of positive and negative charges on the surface of the conductor, inner surface of the conductor of the hole. So, we will have to use a discussion a little later, when I will show you that because of that argument there can be no charges within the cavity of the conductor, on the surface of the cavity of the conductor. So, there can be no electric field inside the conductor, and all the charges are sitting on the outer surface of the conductor. So, effectively what is happening is the inner volume of the conductor within the cavity is completely isolated from electric fields, and this is used to shield components, electronic components, by covering them with a conductor, and you can actually shield the inner area, inner volume from external electric fields. In fact, I can make the cavity bigger and bigger, and finally I will be left with just a surface charge with no conductor, no nothing anywhere. So, the charge is distributed in such a fashion that the electric field inside is 0. So, this charge distribution actually adjusts itself to create a 0 electric field within the conductor, within this volume, and I can actually increase the volume of the cavity to almost touch this outer surface, and all the charges are sitting there. So, a surface charge distribution like this will produce 0 electric field within the volume of this charge distribution. Now, I would like to use Gauss's law to look at the following problem, that is, field produced by a charged conducting sphere. So, my problem is I am given a spherical conductor of radius r, and I have thrown in some excess charge into this. So, the charge which I have excess charge which I have thrown is capital Q, and now my problem is, what is the electric field produced by this charge distribution? So, first thing I know is that the charges are all on the surface. there is no charge inside the conductor. So, all the charges are sitting on the surface. So, first question is, in what way are they distributed on the surface? Are they equally distributed? Are they more on the upper half, less on the lower half? Are they more on the right, less on the right, etc., etc. So, these questions can arise, but I can use, as I mentioned some time back, I can use symmetry present in the problem to get some solutions. So, first thing I notice here is, because I am taking a spherical conductor, all points on the sphere are equivalent to each other. This point is equal to this point, is equal to this point, is equal to this point. All points on the sphere are equivalent to each other, which essentially implies that the charge must be equally distributed across the surface of the conductor. Because if there is excess charge here, why there should be excess charge here, not here? So, if you ask this question, because of symmetry, the charge gets equally distributed across the surface of the conductor and generates the surface charge density sigma is equal to q by 4 pi r square. So, effectively we are looking at a problem in which I have a surface charge density q by 4 pi r square on a spherical surface, and I want to find the field produced by this charge distribution. So, if you recall our discussions with Coulomb's law, what I would have to do in principle is the following. Suppose I were to calculate the electric field at this point, I have to take a small area here, find out the electric field produced by this. I take another small area here, find out the electric field produced by this point. These different areas, how they are producing electric fields, add up all the electric fields produced by all the surface charges present in the sphere and get the total electric field. Now, that is not a simple problem, and here I will show you the power of Gauss's law. So, using Gauss's law, we will be able to immediately calculate the electric field produced by this surface charge distribution. So, how do I use Gauss's law? So, in applying Gauss's law, I must judiciously choose a Gaussian surface. Now, in integral form, remember I wrote an equation like this for the Gauss's law. In this integral form, if I choose an appropriate Gaussian surface, if I can take the electric field out of the integral, which means if I choose a Gaussian surface where the electric field is the same at all points on the Gaussian surface, I can take out the electric field and I will be able to resolve the problem immediately to get the electric field. So, that is what we are going to do here. We will have to choose an appropriate Gaussian surface such that I can integrate that and get the electric field. Now, again I must use again some symmetry arguments. How do I know what is the direction of electric field here? What is the magnitude of electric field here vis-a-vis this point? So, I again use Gauss's law or symmetry now, symmetry considerations. Now, first thing you notice is that because of the spherical symmetry of the problem, the electric field at all points at a given distance from the sphere must be the same. The magnitude of the electric field at a given distance r from the center of the sphere must be the same at all points because of spherical symmetry again. Again as before, if the electric field here is different from here, if I can rotate the spherical charge distribution, then obviously this point will move here, this point will move here, and but the original spherical distribution and the new spherical distribution are exactly the same. So, there can be no difference between electric field here and electric field magnitude here. So, first thing I notice is that the electric field magnitude depends only on r. It cannot depend on the position around the sphere. It will not change as I change from here to here to here as I change my position, but keeping the distance from the center constant, the electric field magnitude will remain the same. So, that is first information I have got. Second one, what is the direction of electric field? Now, electric field here can have a direction in this direction, I can have a tangential direction here, or I can have a direction which is perpendicular to the page. Now, you see again because of spherical symmetry, I cannot have an electric field like this because there is no difference between this direction and this direction. So, if because the spherical distribution is absolutely symmetric about the center, it is spherical symmetry. So, electric field cannot have this component. Similarly, the electric field cannot have a component perpendicular to the page either coming out or going in because of complete symmetry in the problem. So, the only possibility is electric vector is like this. Here electric vector will be like this, here electric vector will be like this. So, electric vector will have to be pointing in a direction which is radial, which is along the line joining the center of the sphere to that point. So, electric field is now becoming radial, it is pointing away from the center of the sphere and it has the same magnitude all across the surface of a sphere of radius small r. So, now having this information, so I can write here E is along r cap. So, r cap is the direction, the radial vector direction. So, this is r cap. The vector unit vector joining the center of the sphere to any point here, that is r cap. Remember, we had introduced this in Coulomb's law. So, from the symmetry of the problem, I have been able to say that electric field magnitude depends only on the distance from the center and the electric vector has to be along the radial direction. So, now let me try to use Gauss's law. So, let me draw the figure again here. This is my sphere with a spherical charge distribution q and I am taking a sphere of radius small r. So, here the electric vector has to be like this and remember the normal is also like this. So, let me go back to this formula E dot dA is equal to q enclosed by epsilon 0. Now, at every point, so dA are elements of area. So, an element of area here, element of area here, element of area here. So, these are all dA directions here, dA direction here, but E is also like this at these points. So, anywhere you choose on the surface of the sphere, E and A are parallel, E and the surface charge surface element are parallel to each other. So, E dot dA is actually nothing but E dA. So, sorry, E dot dA becomes E dA. Now, because I have chosen the Gaussian surface as a sphere and because of symmetry the electric field is the same at every point on the sphere, I can take the electric field out of the integral and I get an equation which is this q enclosed by epsilon 0. Now, this is possible only because electric field happens to be the same at all points on the sphere, because this area, this integral is over the sphere. So, I move my area element from one point to another point on the surface of a sphere and as I move, electric field does not change. Electric field here is magnitude of electric field here, 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 everywhere is the same. So, I can take the electric field outside and what is this? This is the area of the sphere. So, this is E into 4 pi r square is equal to q enclosed, sorry, this is this area is the area of this sphere. So, this is E into 4 pi r square is equal to q enclosed by epsilon 0 and q enclosed is nothing but the charge which I have added to this and that is a by epsilon 0. So, I get the electric field of a charge conducting sphere as E is equal to the magnitude is q by 4 pi epsilon 0 r square and because the direction of the electric vector is along r cap, I get the electric field E is equal to q by 4 pi epsilon 0 r square r cap. So, this is my charge sphere and the electric field at this point is like this along this line. The electric field at this point is along this direction, electric field here is along this direction. So, what is this? So, this is the electric field produced by a charged conductor carrying a charge capital Q. This is also the electric field produced by a point charge of magnitude capital Q at the center of the sphere, because if I had a point charge here, the electric field at any distance would be given by the same equation. So, what I have seen is, please remember I am taking Gaussian surface outside the conducting sphere, because inside the conducting sphere electric field is 0 anyway. So, what I am seeing is that the electric field produced by a charged spherical conductor is the same as the electric field produced by a point charge at the center of the sphere. So, the electric field produced by a charged spherical conductor behaves similar to a charge at the center of the sphere. Now, remember we did not have to do much integration, just because of some symmetry arguments and by an appropriate choice of the Gaussian surface, I was able to take the electric field out of the integral and integrate the area and get the electric field as a function of position. So, this is a very interesting. So, as you can see here, the power of Gauss's law here, that by using symmetry arguments I can calculate the electric field of a spherically charged distribution. I can also put this in a slightly different form. Remember, Q is the total charge, and I mentioned that it is uniformly distributed on the surface of the sphere. So, the surface charge density is the total charge by 4 pi r square. This is surface charge density, and so if I calculate the electric field very close to the surface of the conductor, just outside, r is equal to capital R. So, electric field will be Q by 4 pi epsilon 0 r square into r, which is equal to sigma by epsilon 0 into r cap. So, r cap is nothing but the unit, it is a normal vector. So, this is actually also equal to sigma by epsilon 0 into n cap. So, what it implies is at every point, at this point there is a electric field sigma by epsilon 0 pointing in this direction, sigma by epsilon 0, sigma by epsilon 0, sigma by epsilon 0, sigma by epsilon 0. So, actually this is a more general result we will see later on. If you have a charge, surface charge here, it produces an electric field, and we will calculate the electric field produced by surface charge density. And in this conducting case, in the conductor case, where the electric field is 0 inside and outside, it is sigma by epsilon 0 into n cap. So, this is a very interesting example where we have seen the power of Gauss's law in being able to calculate the electric field produced by a charged conductor. So, inside the conductor the electric field is 0, and outside the conductor the electric field produced is exactly the same as if the charge was concentrated at the center of the sphere. You may have come across a similar situation in studying gravitation. The gravitational attraction of a spherical mass distribution is exactly the same as if the entire mass was concentrated at the center of the spherical distribution. Because the two forces, gravitational force and electrostatic forces, follow similar laws, the results are very similar. Now, I want to look at another example, and in that example I will be able to calculate by using Coulomb's law and by using Gauss's law, and there again you will see how Gauss's law simplifies the calculation. So, this is the field due to a line charge density, and I am assuming infinitely long. So, I have a line, a straight line which carries a charge per unit length lambda. So, lambda is the charge per unit length of this charge line charge distribution, and my objective is to calculate the electric field produced by this line charge. Now, I am considering an infinitely long line charge. Obviously, infinite line charge do not exist, but if you have a very long line charge very close to the line charge distribution, the line charge distribution will behave as if it was infinitely long. So, my objective is to find what is the electric field at this point, at some point. So, what do? I drop, first let me use Coulomb's law to try to calculate what is the electric field here. I will have to do some integration, and then later on I will show you the Gauss's law, the power of Gauss's law. So, I drop a perpendicular here, and so let me call this as z axis. This is some point here, let me call this distance r from here. Now, please note that this point is the same as this point, because of infinitely long line charge, all points at any value of z if you choose, it is the same. So, I am calculating at some point, and as you will see, because of again symmetry, the electric field here and here will be the same, because it is z invariant system. The charge does not, as you move along the z axis, nothing happens. Okay. So, now let me take a small element of charge here of length dz, and the electric field produced by this charge will be along this direction. Let me assume a positive charge. You can do the same calculation with negative charges. Electric fields will be pointing towards the charge. Here I am just for simplicity or for this for specific problem, I am considering a positive charge density. Please note that so this is at distance z from the axis. A distance z on the other side also I can have an element. Now this element will produce an electric field like this. This distance equal to this distance, this charge is equal to this charge. So this electric field and this electric field are exactly equal in magnitude. So you can see it will have a horizontal component and a vertical component. This will have a horizontal component and a vertical component. The vertical component, these angles are equal, all these angles are equal. So this vertical component of this and vertical component of this are exactly equal and in opposite direction. The horizontal component of this and horizontal component of this again are equal, but in the same direction. So the electric field at this point will be oriented in this direction, because these two components cancel off each other. So that is one thing which I have seen already from this distribution, but let me now calculate what is the electric field produced here by this. So what I will have to do is essentially get only the horizontal component finally, because that is what is going to add, and the vertical components at any point the vertical component of electric field will become 0, because for every element of charge that creates a upward component, there will be another identical charge element which will create a downward component of equal magnitude. So it will cancel off. So let me calculate the magnitude of this electric field. So let me call this dE. Magnitude of electric field is charge here, which is lambda dz. Lambda is the charge per unit length multiplied by the length which I am taking. Lambda dz is the charge contained in this, divided by 4 pi epsilon 0 into this distance square. So let me call it small s square. That is the magnitude of electric field produced here, and its horizontal component, if I call this theta. So this is only the horizontal component, this is not the total magnitude. Total magnitude is this charge divided by 4 pi epsilon 0 times distance square. Its horizontal component is multiplied by cos theta, because the vertical component, which is sin theta, is going to cancel off. And what is s square? S square is nothing but r square plus z square. So dE is equal to lambda dz by 4 pi epsilon 0 r square plus z square into cos theta. Now cos theta, let me calculate, this is theta, this is this theta. So cos theta is nothing but r by square root of r square plus z square, r by square root of s square plus r square plus z square, which is this distance, and that is cos theta. So this is lambda dz by 4 pi epsilon 0 s square, which is r square plus z square into cos theta. So this is the horizontal component, and as I mentioned, I do not worry about the vertical component. So let me simplify this. So dE becomes lambda dz by 4 pi epsilon 0, and there is r here, r square plus z square raised to the power 3 by 2. So this is the magnitude of the horizontal component of the electric field produced by a small elementary length dz of the line charge distribution. So how do I calculate the total? I integrate over the entire length of the charge distribution, and please remember that all the charge distributions I am only integrating the horizontal component. So the horizontal component produced by all the elementary charge distribution are in the same direction. So I just add the magnitudes rather than the direction. If I were to calculate the total electric field, I must integrate, making sure that I am adding the vectors, but here because I am calculating the horizontal component of each element will be along the same direction, and I am just adding it up. So the total electric field magnitude will be equal to lambda r by 4 pi epsilon 0 integral dz by r square plus z square raised to the power 3 by 2, and dz goes from minus infinity to plus infinity. So, z position, which is the position of this point from the perpendicular drop from this point where I am calculating. So, z goes from minus infinity on the bottom side to plus infinity on the top side. Now, that is a very standard integral. So, all I have to do is to do a small change of variables. So, I write z is equal to r tan phi. So, dz will be equal to r secant square phi d phi, and r square plus z square will be equal to r square plus r square tan square phi, which is equal to r square secant square phi. So, E becomes, I can write an expression for E. So, E becomes lambda r by 4 pi epsilon 0 integral. Now, there was a dz on the top. So, I will have to write r secant square phi d phi. There is r square plus z square is for 3 by 2 in the denominator. So, I will get r cube secant cube phi. Now, look at the variable change. If z is minus infinity, phi is minus pi by 2. If z is plus infinity, phi is plus pi by 2, because tan pi by 2 is infinity, tan minus pi by 2 is minus infinity. So, the integration variable from minus infinity to plus infinity in z becomes minus pi by 2 to plus pi by 2 in this variable pi phi. So, minus pi by 2 to plus pi by 2. So, some things cancel off here. So, I get lambda, there are r square. So, lambda by 4 pi epsilon 0 r into integral minus pi by 2 to plus pi by 2. This is nothing but cos phi d phi, which is equal to lambda by 4 pi epsilon 0 r sin phi minus pi by 2 to plus pi by 2, which is nothing but 2. So, this lambda by 2 pi epsilon 0 r. So, please note my integration goes from minus infinity to plus infinity. So, I have taken into account all charges present on the line charge, and so this is the total electric field produced, and I know the direction of this, because as I showed you in the figure here, the direction will have to be in this direction. So, let me call this r cap. So, I will have the electric field produced by an infinitely long line charge distribution is at this point will be like this, and E will be like this, and that is equal to lambda by 2 pi epsilon 0 r, where this distance is r and this will be r cap. And this is the line charge distribution with charge per unit length as lambda. So, compared to a point charge where the electric field decreased as 1 by r square, in this case the electric field decreases as 1 by r, distance r is the distance of that point from the line charge, and it is along the direction of the perpendicular drawn from the point where you are calculating the electric field to the line charge distribution. So, you have seen a little bit of mathematical calculation to find out the total electric field at this point because of the entire line charge distribution. Now, let me try to solve the problem using Gauss's law. So, I go back and look at my problem again. So, I have this infinitely long line charge distribution, charge density lambda, and I want to calculate the electric field at some point. Now, what do I do? As before, I must use some symmetry arguments to find out the possible direction of the electric vector and choose a Gaussian surface on which the electric field remains constant. Okay. So, first thing I note is as you see here, electric field cannot have this component, as you have already seen by symmetry arguments, because of electric fields from two different elements cancelling off the normal component. There cannot be this component. Even otherwise, there cannot be a component here, because there is nothing in the line charge distribution which differentiates the upper direction from the lower direction, because this is fixed. There is nothing which says that this is different from this. So, there cannot be a component of electric field in the vertical direction. There cannot be a component of electric field perpendicular to the plane of the page, because if it is coming out of the page, why can't it go into the page? So, there is no difference between coming out and going in. So, there cannot be any electric field distribution in that direction. So, the only possibility is electric vector is like this. It has to be along the direction. If I drop a perpendicular from here on the line charge, electric field here, electric field will be, if I drop a perpendicular, it will be like this. Here at this point, I drop a, it will be like this. So, electric field has to be pointing away from this line charge, because it is a positive line charge distribution. If it was negative, all the vectors will be pointing towards the line charge, and so electric field will be pointing away from the line charge. That is first thing. Second, you see here that if you take a circle with the line charge at the center, circle having a radius r, electric field at these points must be the same, because there is no difference between this point and this point and this point and this point. They are all the same, because there is no difference, there is nothing which differentiates this position from this position or this position. So, electric field magnitude must be the same at all these points. They are in the respective directions away from the line charge, but they have to be equal in magnitude. So, I have got a line in which I know the electric field is the same. I have got the vector direction of electric field. So, now I choose my Gaussian surface. So, this is my line charge. I choose a Gaussian surface like this. So, this is lambda and this is my Gaussian surface. It is cylindrical with the center as the line charge of radius r. This is the upper surface, there is a lower surface here, and this is a cylinder surrounding the line charge distribution of radius r with the line charge at the center of the cylinder. So, now I know first thing is that the electric field at this point will be pointing away from the surface of the cylinder, normal to the surface of the cylinder, they are all. Second, the electric field on the upper surface is tangential to the surface. The electric field on the bottom surface is tangential to the surface. So, remember when we introduced flux, we said it is dot product of the electric vector and the area vector. On the upper surface, area vector is like this, electric field is parallel to the surface. So, the dot product is 0. Here the outward normal is like this and the electric field is like this. So, there is no flux crossing the upper surface of the cylinder and the lower surface of the cylinder. The only flux that is crossing is through the cylindrical surface of the cylinder, and on all points on the surface of the cylinder, the electric field magnitude is the same. Number 1. Number 2, electric field is always at all points along the normal to the cylindrical surface. So, all I need to do is, because the electric field is constant on the cylindrical surface and it is along the same direction as the normal at every point on the surface, the Gauss's law will tell me E magnitude into the surface area of the cylinder, which is 2 pi r into if the length of the cylinder is L, is equal to charge enclosed by epsilon 0. And what is the charge enclosed? Charge per unit length is L, this is the length L, sorry, charge per unit length is lambda, this is the length L of the wire. So, charge enclosed is lambda into L by epsilon 0. So, that gives me immediately an expression for the electric field, E is equal to lambda by 2 pi epsilon 0 r. So, this is the distance r, and the magnitude, the vector is along this direction. So, let me go back and look at what was the expression I got before. This was the expression which I got by integration of the total charge, total electric field from Coulomb's law. That is the expression which I got from Gauss's law, and you can see how much more simplified Gauss's law application was in this case, and that is because I am using some symmetry arguments. I am finding out from the symmetry arguments what could be the orientation of the electric vector. I am then taking a Gaussian surface on which the electric vector magnitude remains constant, and that helps me to pull out the electric field out of the integral of the Gauss's law and help me to calculate the Gauss's help me calculate electric field using the Gauss's law. So, this is a very powerful method to calculate, especially when there are symmetries in the system. Now, let me go to another interesting problem, which is another example, field due to an infinite sheet of surface charge. Sigma. So, I am taking an infinite sheet with surface charge sigma, charge per unit area, and let me again assume this will be positively charged. What is the electric field produced by this? So, in fact, I can again use Coulomb's law to calculate the electric field of this charge distribution, but I will use Gauss's law now to calculate what is the electric field produced by this infinite charge distribution, surface charge distribution of sigma. Now, again I must use some symmetry arguments about the direction of the electric field and the magnitude of the electric field. As you can see, because the surface charge distribution is infinite in size, all points at a given distance from the surface charge, they are all identical. There is no difference between this point at a distance d from the surface charge, this point which is d from the surface charge. Please remember, I am considering an infinitely large surface charge distribution. It is not a finite charge distribution, it is an infinitely large surface area. So, I can actually first thing I know is the electric field should only depend on, it cannot depend on this position here. So, anywhere in front, so if I had a plane surface like this, if I had a plane charge density charge distribution like this, the electric field at this point, at this point, at this point, they must all be the same in the same direction, same magnitude, because there is no difference between this point and this point and this point. Similarly, on the other side, because it will just depend on the distance from the surface charge distribution. What about the direction of the electric vector? Now, again, as before, you can see electric vector cannot have this component, because if it had that component, why does not it have this component? Why does not it have this component? Why does not it have other component? Because all directions are exactly the same. There is no difference between up and down or between left and right if there is an infinitely big surface charge distribution. So, there cannot be a component which is perpendicular. So, if I drop a perpendicular from this point on the surface charge, then there cannot be a component perpendicular to the line, that line, because of symmetry simply. So, the electric vector has to be pointing perpendicular to the surface charge. So, if I again draw the surface charge distribution, then at any point here electric field has to be like this, at this point it will be like this, at this point it will be like this, and so on. And similarly, on the other side, if I look at like this, and this is positive. So, symmetry tells me electric field has to be normal to the surface. Symmetry tells me electric field can only depend on the distance, if at all, from the plane. And using these two, I have to judiciously choose a Gaussian surface which will help me to calculate the electric field. So, the Gaussian surface I choose is as follows. So, I take a cylindrical box of area A, and the cylinder is normal to this plane surface, and it is a cylinder intersecting the surface perpendicular. So, this line is perpendicular, and it is this plane is passing to the center of the cylinder. So, this length is equal to this length. So, now let me look at what is the flux coming out of this closed surface. The closed surface consists of these two flat surfaces here and a cylindrical surface connecting these two surfaces. Passing through the surface charge density, such that the center, the plane surface charge density is intersecting the cylinder right through the center of the cylinder. Now, as we have already argued, electric vector has to be normal to the plane. So, electric vector at all points will be like this, and you see on the cylindrical surface the normal is perpendicular. So, there can be no flux coming out from the cylindrical surface of the Gaussian surface, because the normal to the cylindrical surface is at every point perpendicular to the electric field vector, and so E dot dA will be 0 at every point on the cylindrical surface. So, the only flux that can be coming out is from the two areas on either side, and so the total flux will be, and secondly I also know that the electric field at every point on the flat surface will be the same, because they are all at the same distance from the cylinder, from the surface charge density. So, all these points are at the same distance from the surface charge density, all these points are at the same distance from the surface charge density. The electric field magnitude here and electric field magnitude here are equal. The electric field magnitude at every point on the surface is equal to electric field magnitude at every point on the surface. So, the total flux, total electric flux will be equal to electric field into one area here and one area there. Here the electric flux is coming out, here the electric field is coming out. So, the total electric flux is E times 2 A, and total enclosed charge sigma times A, because sigma is the charge per unit area. So, this cylinder will intersect an area A on the surface charge density, which will then carry a charge sigma A. So, I get, if I use Gauss's law, this is the total flux, this is the total charge enclosed. So, total flux must be equal to total charge enclosed by epsilon 0, which gives me E is equal to sigma by 2 epsilon 0. And if I draw this surface like this, let me draw the surface like this, and if this is the direction, if I call this as some n cap direction. So, this is nothing but, so this n cap vector is perpendicular to the flat surface. So, this is the plane here. So, electric field at every point is pointing away from the flat surface charge distribution and has a magnitude sigma by 2 epsilon 0. It is interesting to note that the electric field is independent of the distance from the surface charge. Now, you might ask, how can this happen? Because if I am very far away from the surface charge, the electric field must be 0, but because this is happening because I am taking an infinitely sized surface charge distribution, the surface charge is everywhere in the entire infinite plane, and the electric field remains constant as you move away from the surface charge distribution and has a magnitude sigma by 2 epsilon 0. So, there is electric field. So, if I had this, if I had a flat here, so here at this point the electric field is sigma by 2 epsilon 0 in this direction, at this point electric field is sigma by 2 epsilon 0 in this direction, at this point it is sigma by 2 epsilon 0 at this in this direction, and so on. So, every point electric field is sigma by 2 epsilon 0 pointing away from the flat charge distribution. If it was a negative charge distribution, they will all be pointing towards the charge distribution. So, as you can see here, because of Gauss's law, I could very quickly calculate. So, I have to use initially some symmetry arguments, which will help me to choose an appropriate Gaussian surface, and once having chosen appropriate Gaussian surface on which the electric field magnitude remains constant, I can then take the integral, take the electric field out of the integral in Gauss's law, and it is easy for me then to calculate the total flux, electric flux coming out of the closed surface, and with that calculation I am able to immediately estimate what is the electric field. So, one example which we looked at was a spherical charge distribution, one was a line charge distribution, and this is a flat charge distribution. I can extend this to little more interesting problems. For example, if I take a thin conducting plate So, if my conducting plate is like this and I have thrown a surface charge q into it. So, this is conductor. So, as we discussed before, if this is plus q, there are plus charges sitting here on this surface, there are plus charges sitting here on this surface. So, it produces some surface charge density sigma here and sigma here, everything everywhere it is positive charge. So, assume that this is a very huge plate, thin plate, and I am sort of neglecting the ends of the plate and assuming that there is a surface charge density sigma on the left surface and a surface charge density sigma on the right surface. Now, you see this surface charge density produces an electric field, this surface charge density produces an electric field, and what you observe is the sum of the electric fields produced by this surface charge density and this surface charge density. So, let me look at the surface charge density on the left. So, this produces sigma by 2 epsilon 0 here, it produces sigma by 2 epsilon 0 here. So, let me draw another bigger figure. So, there are plus charges sitting here, there are plus charges sitting here. So, this produces sigma by 2 epsilon 0 in this direction, sigma by 2 epsilon 0 in this direction. This charge produces sigma by 2 epsilon 0 in this direction and sigma by 2 epsilon 0 in this. This charge also produces sigma by 2 epsilon 0 here. This charge also produces sigma by 2 epsilon 0 here. So, what is going to happen inside, you see here that this sigma by 2 epsilon 0 produced by this surface charge density and this sigma by 2 epsilon 0 produced by this surface charge density are exactly equal and opposite to each other, cancelling off and producing electric field is equal to 0 inside the conductor. So, as you can see here in this problem, the charges, if it is a solid conductor, the charges in this problem would equally distribute on the front and the back surface, this surface and this surface. So, that the field produced by this surface charge density and the field produced by this surface charge density are exactly equal and opposite and cancel each other off to produce 0 electric field inside. Here the total electric field will be sum of the electric fields, which is sigma by epsilon 0 here and there is sigma by epsilon 0 here. The net electric field is this here on this side and sigma by epsilon 0 on the other side. So, from these charge distributions actually I can calculate the net charge distributions. Now, let me look at another example which we will come to later in capacitors. So, I have the following problem. I have two plates, plus charge density here and minus charge density here. So, sigma and sigma, this is minus sigma. Now, these are two conductors. So, this produces an electric field sigma by 2 epsilon 0 here, this produces an electric field sigma by 2 epsilon 0. Please note this is positive charge. So, electric field is pointing away from this charge, this is negative charge, electric field is pointing towards the charge. At this plane, this plus produces sigma by 2 epsilon 0. So, and this one produces sigma by 2 epsilon 0 on the other side. So, the sign I am taking by drawing an arrow in the opposite direction. Okay. The magnitude is sigma by 2 epsilon 0, one is positive charge produces electric field like this, negative charge produces like this. Similarly, here the positive charge produces sigma by 2 epsilon 0 here and the negative charge produces sigma by 2 epsilon 0. So, you can see that the net is 0 everywhere including inside except in this region where the field becomes sigma by epsilon 0. The two fields add here, the two fields cancel everywhere else. So, we see a similar situation in a capacitor problem where we bring in two conductors facing each other carrying some charges, and as you will see that the charges. So, the positive charge attracts the negative charge to this side, the negative charge attracts the positive charge to this side, the charges set up such that electric field inside the conductors is 0 and the electric field exists only within the spacing between the two conductors, and that will, as we will see later on, forms a very important element in electrostatics, which is the capacitor problem. So, what we have seen is that you can use Gauss's law to calculate electric fields produced by charge distribution by choosing an appropriate Gaussian surface. We must use the symmetry present in the problem to help us to calculate the integral total flux, and once I know the total flux, if the electric field I do not know, I still can calculate the total flux, and by symmetry if I can do that, then I can calculate the electric field produced by the charge distribution, and as we have seen in some of these. So, it is useful in symmetric situations, but let me again tell you, Gauss's law is always valid whether there is symmetry or there is no symmetry. The electric flux coming out from any closed surface, if I take any closed surface S, integral E dot dA is always equal to Q enclosed by epsilon 0. So, the total flux coming out from any closed surface is the charge enclosed by epsilon 0. If the flux is 0, it does not imply 0 electric field, it only implies that the net charge is 0. So, I will leave a problem at the end of my talk here for you to think about. Positive charge Q is distributed uniformly throughout the volume of an insulating sphere of radius r. Using Gauss's law, obtain the electric field inside and outside the sphere. And you can compare this problem with the gravitational field produced by a mass, spherical mass, which is uniformly distributed across the volume of the sphere. Thank you very much.